So, I said recursive optimality is good if you have a mechanism by which you can treat the solutions that you have as action, so that your horizon, your learning horizon becomes smaller, right. I do not really have to look for many actions to come before I make a, before I can learn something new, right. Otherwise, I said it will not be a very useful thing. So, one of the foundational structures that we use for doing that is called a semi-Markov decision process. So, what is a semi-Markov decision process or a semi-Markov decision process?
Depends on not just, it might depend on two or more states, a few previous states.
No. No, that is just non-Markov, it is like nth order Markov. If it depends on two previous states, it is a second order Markov. So, in semi-Markov decision processes, right. So, in a Markov process, what do you have? So, I have a state ST, I take an action AT, then I go to ST plus 1, I get RT plus 1, right. So, and this happens again and again. So, next I take an action right, it keeps going. After I receive RT plus 2. So, you guys can see my font from there, right? Okay. So, in semi-Markov decision process, what happens is I am in ST, I take AT, then some time elapses, I find myself in the next state at time t plus tau. So, where tau is some kind of a random variable that is sampled based on ST and AT, right. I also get some reward t plus tau. Now, I take another action it is not t plus 2 tau, okay, it is t plus tau plus some other time tau prime.
What is time bother about?
Huh?
We are nowhere bothered about time.
We are bothered about the time, right. So, because we use gamma power.
Because we are always thinking in terms of returns and the
Sorry?
return doesn't change.
Huh?
Return doesn't change how much ever the time frame is. But that will be.
So, I will use gamma power t RT plus 1, right, gamma power 1, right, basically, right. I will use gamma into RT plus 1 or no, sorry, gamma into RT plus 2, gamma squared into RT plus 3 and so on and so forth. Now, what I will do is I will use gamma power tau into RT plus tau plus gamma power tau prime, tau plus tau prime into whatever is the next r and so on and so forth. And the next time I do the same actions, right, the time taken might be different. So, now I am not only interested in what the next state I am going to land up in, is how long will it take me to get to the next state, because that is how much I am going to discount the reward by.
Instead, we can push that into the subproblem itself and let the subproblem solve it.
How do you get to subproblem? No, maybe that's the best way to solve the subproblem. It takes you 5 time units to solve one subproblem. Right. So, I am not even talking about any subproblems here, by the way. You are getting ahead of yourself. Okay. This is just a semi-Markov decision process. There are no subproblems here. There are only states and actions. Okay. There are no subproblems here. I am just saying actions take different amounts of time to complete. So optimality now would depend not only on where the action takes me, but how long it takes to get there, how long it takes to get there, right?
Explain the tau.
What is it?
Explain the tau.
Explain the tau. Tau is just the time taken for the action to complete.
It's a random variable.
It's a random variable. So every time I take an action, it may take a differing amount of times to complete.
So the state where we do end up in,
Uh-huh.
is that
Dependent on tau.
yeah.
In reality, it would. In many cases, it would. But we kind of wave our hands here and decouple the tau and the S prime distributions. Right. So typically, we end up decoupling the tau and S prime distribution. So it makes it a little easier. But typically, it should be a joint distribution. Right. So historically, SMDP models used to do that. Right. But then Tom Dietrich introduced a variant of the SMDP model into the literature, specifically meant for modeling hierarchies. Right, where he actually defines the distribution as joint distribution over tau and S prime. Right. So historically, so people used to talk about this as holding time. I keep saying historically, people who use SMDPs in OR and other things will kill me, because that is how they use it even today, right. So it is called holding time, right. So holding time, essentially the idea is that at time t I decide A is the action I am going to take, right, but I do not apply the action A till t plus tau.
What possible purpose could it serve for you to hold the action for?
It could be a variety of reasons. I mean, I could actually be sensing the market at some point of time, and by the time I place my order, it might be 15 seconds later, or 20 seconds later, or 30 seconds later. There could be a variety of things that come in this. There could be many reasons why you want to do that. I mean, you could there should be gap between the sensory input coming to you, right, and you taking an action, right. So it's semi-Markov in the sense that for the duration of the action, I don't know how the system is evolving. Right. So to determine when the next state is going to occur, I really need to know how much time has elapsed since the last state was seen. Right. So some amount of history dependence is there. So that is why it is called semi-Markov. Right. So I know that tau seconds have to elapse before the next state happens, right, but how much of the tau seconds is left? Right. So that is why it becomes semi-Markov, not completely non-Markov, because once this has happened, the probability of ST plus tau depends only on ST and AT, right. But during this transition, when this will actually show up, right, depends on how much time has elapsed. Okay. So it is only for this brief periods you have the time dependency. Okay.
We see tau has two different cases. One is after taking action, how much time does it take for the next state to appear?
Yeah.
And how much time we wait before taking the action?
That is just semantics, right. So some people refer to it as holding time. Holding time is when you actually, when do you apply the action, right. Other one is, you can think of it as transition time. So I apply the action immediately, how long does it take for the next state to actually happen? That is like a transition time.
So both
Right.
mean the same.
Both mean the same thing. So for RL people, its transition time makes more sense, right. But in the other the holding time explanation was given only because of the semantics of things, right. So what really happens if I already applied the action, what happens to the system after the action is applied? So instead of asking that question, you say, okay, I will stay in this state for tau seconds and then I will apply the action, immediately I will get the next state. So there you kind of sidestep the question of what happens after you apply the action and before the next state turns up. But we do not want to sidestep the question. I apply the action, go to room 1, and I want to know what happens after that, right. So I will pay attention to this. So that is why the transition time definition is more acceptable for RL folks, right. So we have some more time. So the SMDP is defined as the tuple S A P R
So the holding time and transition time aren't they different, because I'll sense a state and before I take
see the thing is, these are explanations, these are models that you have, right. So, this is this. At the end of it, mathematically what is happening is there is a state that occurs at time t, there is a state that appears at time t plus tau, okay. That is it. So, what happens in between, people come up with different ways of interpreting that. See, one way that says that, okay, I actually apply the action at time t itself and it takes the system some time to evolve and settle down into st plus tau.
These three are three different types of modelings, aren't they?
In what way?
Say if we are assuming that action will be applied as soon as it sends and the state doesn't change before I apply the action. That is one way of modeling. Another way is the state changes before I apply, but as soon as I apply, the state changes.
Generally we assume the state stays for time tau, that is why it is holding time. So, you come to a state, you hold the state for tau seconds and then I apply the action, I go to the new state.
So, as soon as I apply action, I
go to the new state. The other one is,
but in some cases we will have both kind of delays.
it does not matter. See, the point about SMDP is I really do not tell you what happens in those tau seconds, right, and you can interpret it different ways, but mathematically you end up with the same thing. See, the quantities I am using for modeling, as I will write it down now, you will see what I am going to say, that eventually end up with the same thing, right. In fact, the holding time interpretation says the following: I see ST, I pick AT immediately, but I wait for tau seconds before I apply it, right. So, the decision is made before the waiting time starts, before the holding time starts, so that the holding time is still a function of the decision, okay. So, I have SAPR, so we know S, we know A, so we know all of this from the standard thing. So, P is defined as the following: P I define P of S comma tau given S, is S prime comma tau given S comma A. So, earlier our probability distribution was S given S prime given S comma A, now it is S prime comma tau given S comma A, right, and the reward becomes expected value of R given S A, S prime and tau. So, why does a tau figure in? I mean, because it will actually end up getting some kind of discounting, or so it could be accumulating some rewards along the way, it could be just the waiting time. So, for every second you wait, you accrue reward at a rate of -1 per second or something, right. So, you could give some kind of a rate of reward, right. So, it could be some R, minus R is the rate of reward, and then if I am waiting for tau seconds, and basically I do an integral over that to get you the total sum of the reward, right, the rate is minus R, right. So, I could get some, so things like that, right. So, the reward that I get could depend on the transition time or the holding time and so on and so forth. So, earlier people used to write this as two different functions. So, they right, notice that this is not a perfect decomposition of that, right. I am assuming tau is independent of S prime. So, if I actually had used the product rule to decompose it, tau should have been dependent on S prime, or S prime should have been dependent on tau, one way or the other, right. So, but now I am just saying this. So, this is the classical way, let me not put it in the earlier way, it is a classical way of writing the SMDP transition dynamics as into two components, one on the tau, one on the S prime.
Easier to mathematically implement this one, the classical one.
Yeah, but this is more meaningful for the RL domain.
Joint probability will be
But it is more meaningful for the RL domain because depends on what is the problem that where I am going to land up in, right, the time that I am going to take. For example, if I am going to go out through A or go out through B, right, the time taken will be different for executing it. Start from the same state, if I am choosing to go out through A, it will have some time, if I am choosing to go out through B, it will have a different time. So, depending on which S prime I am going to go for, the tau will be different, right. So, those things should matter, right. So I can't do a separate distribution like this. I have to do a joint distribution over S prime and tau. Okay. Any questions on SMDPs? All of it clear, right? We can write SMDP value functions. You can write SMDP Bellman equations. I hope all of you can write that. Can you write SMDP Bellman equations? Well, depends if you can write SMDP value functions first. Right? Write the value function and then write the recursive version of the value function, right? And then convert that into a Bellman equation. How do you decide on the what gamma? Gamma is, well, that's the same problem with all discounted reward formulations, right? Gamma has to come from the domain expert.
I'm saying like gamma, like every time step you put as gamma 1 comes like gamma.
Yeah.
It should be tau or something.
The expectation has to be over the tau also. So it becomes, it's not very hard. It's a little tricky to write this thing, but it's not too hard. You can write it. Right? So I'm leaving it as an exercise. I'm going to leave all of you to go and look up Bellman optimality equation, or rather the Bellman equation for SMDP. Can you put that recent advances in hierarchical RL paper, Barto and Mahadevan? Right. So there are a lot of hierarchical RL frameworks that have been proposed in the literature, and surprisingly, you would get more information about these frameworks by reading a survey paper that was written a little later after all these all the architectures are proposed, than reading the original papers themselves, right. So there are two reasons for it. So kind of the authors of the survey paper had a little bit more perspective, so they could see all the things together in a unifying framework and they could present it in a better fashion. And of course I am very biased, and therefore the one of the authors of the survey paper is a fantastic writer, and therefore he wrote a better paper than the original writers themselves, right. So it's my advisor, so of course I am biased. So read that paper. So recent advances in hierarchical RL, and so he describes SMDP and SMDP value functions and everything very beautifully in the paper, right. And then I am going to talk about a few other things that we can do. First thing I want to talk about is something called SMDP Q-learning, right. So what do you think is SMDP Q-learning? Is it plus minus 1? Do we need a minus 1 there? Yeah. Huh?
Should there be a T as well in the gamma? Gamma
We are
power.
now writing just gamma. Tau minus.
You're right.
Why tau minus
Why
1?
minus 1?
Tau times steps. If tau is 1, I do gamma, right?
Yeah. So 1 times.
Then it will be
step, right?
tau only, right?
If tau is 1, I do gamma. Okay, stop. right. So that's basically SMDP Q-learning. It looks very simple, right? It's just that the rewards are discounted. So the tricky thing here is I have hidden some stuff into this RT plus tau, right. So what is RT plus tau? Right. So it's the expected reward that I am going to get over the tau time steps. Right. It's not expected reward, it's still a sample, right. I just taken a sample over tau time steps. So it could be variety of things, right. So normally in the classical SMDP framework, we don't tell you how this tau plus RT plus tau comes about. So you have some mechanism by which you can generate it, right. It could be some e power r tau integral 0 to tau, okay, e power r something RT integral 0 to tau d tau. Right, so that could be one way of defining this. So that's a rate function. So r is a rate function, and I accumulate that function for tau time steps, right, and that gives you a reward, right. But what we are more interested in is to actually think of r t plus tau as okay. So this RT plus tau is our usual RT, right. So the reward, the one step reward that you get tau time steps after you took the action, right. So maybe this makes it clearer. Okay, so I am not written something that is recursive, so maybe there you go. So r bar t plus tau is essentially the return I have accumulated for the tau time steps after I have chosen action AT. So in some sense, if you think about this two world example, so I will start here, let us say, and then I say do B, go to room 2, right. Then it is basically the reward I get for till that point, right, and the value of go to room 2 here will get updated by the value of the state here, right. So I will take the Q here and do the max over A, right, and for the r bar t plus tau I will use all the rewards I get till that point. That will you take both those quantities and then update the Q of go to room 2 here. Make sense? Okay, so this is called SMDP Q-learning.
This RT in a way is solving a multi-objective problem of minimizing time apart from maximizing.
Sorry?
Are you minimizing time in any way?
It depends on the reward function. If the reward function is the usual -1 per time step reward function, then you are minimizing time. Or if the reward function is also 1 when you reach the goal and gamma discount along the way, then also you will be minimizing time, except that for this action RT plus tau will be r bar t plus tau will always be 0, right, because you will get no reward, but then slowly your reward will start propagating back. Okay. So notice that SMDP Q-learning does not actually look into the structure of AT, right. It just assumes that this reward somehow comes when I take action AT. Okay. So it assumes that AT has been learnt already. So what is AT here in this example? Go to room 2. AT was go to room 2, right. So it is not a simple action. This is what we mean by the temporal abstraction. So when I say go to room 2, it actually takes some 10 time steps to go to room 2. If I had said go to room 2 from here, it would have just taken 2 time steps to go to room 2. So it would be different. right, and there is some kind of stochasticity in the world, right. So let us say with probability 0.9 my action will succeed, right, otherwise it will fail, then it will take different amount of time, even from the same state. If I say go to room 2, it will take different amounts of time to complete. So that is basically it. So we will stop here with SMDP Q-learning. So from next class I will actually look into the different hierarchical architectures that are available, and then we will see how we can modify SMDP Q-learning to work with different architectures.
So the R bar T plus tau, right? Why we define that as a discounted sum of rewards? Can that be defined? Would it be better to define it as average or like the sum of the total rewards?
Choose whatever you want. SMDP Q-learning defines it like this because it's defined on the discounted return. So eventually at the end of the day you would still want to solve for the discounted return, right, because you are trying to optimize the discounted return eventually, right. So if you are trying to optimize average return, then you can define your reward functions differently.